This video is dealing with our next reaction type, the decomposition reaction. Again, our learning target for all of the reaction types is that you can determine which type of reaction it is simply by the reactants given. So when we think about a decomposition reaction, if you call to mind words that you can think of that have decomposition as part of the title, we can think of decomposing bodies. Yes, that's the first one that comes to mind. The decomposition of a compost pile. But basically, anytime you come up with decomposition, you'll probably come up with an example where things are falling apart. Okay. So here's your pictorial representation. That's kind of hysterical. When you think of a decomposition reaction, basically, whatever the whole is, it falls apart into its component pieces. Okay? Similar to the decomposition of fruit in a compost pile. Whatever that whole is, the strawberry, for example, it's going to fall apart into its smaller molecules rather than the full form of a strawberry. So a decomposition reaction then in terms of a chemical term would be a whole, and usually we think of a whole as a compound because it has multiple pieces that can break up into something smaller, which we can say is their elements. Okay, or potentially a few simpler compounds depending on the situation. So your general formula for a decomposition reaction then is having a compound, AB, fall apart into its single components, A plus B. If you look at that, that's just a reversed synthesis reaction. Right? Synthesis is taking AB and making the compound AB, and decomposition is taking the compound AB and having it fall apart into A and B. So the reactions I showed you for synthesis, if you do the reverse of them, that's decomposition. But here's a couple other examples. Water can decompose into hydrogen and oxygen. And if you have like mercury oxide, for example, that can fall apart into mercury and oxygen. In all of these cases, don't forget about your diatomics, HNOF17. So when I say it forms hydrogen, I do mean H2. The way you'll be able to identify them in regards to that learning target is if you look at the reactants and you see a compound, just one lone compound, that is a decomposition reaction. We will assume these reactions always happen. There's no other rules we need to consider, but there are exceptions to how things decompose, same as there were exceptions to how things synthesize. So here are your special types or your special exceptions. If we're dealing with a metal carbonate, so a metal bonded with carbonate, rather than falling apart into the metal and carbonate, it falls apart into metal oxide and carbon dioxide. If you're dealing with a metal chlorate, so that's a metal bonded with the polyatomic chlorate, it will decompose into a metal chloride and oxygen gas. And if you're dealing with a metal hydroxide, so that's a metal bonded to hydroxide, it'll decompose into a metal oxide and water. So these are three cases that you'll simply have to memorize so that if you are presented with a metal carbonate, a metal chlorate, or a metal hydroxide, you will understand how they break apart. Now, if you see all three of these cases, these are polyatomics. Generally speaking, when we're dealing with polyatomics, they won't decompose into just their two component pieces like they did for water or for that mercury oxide. But generally speaking, you should assume that they're going to break up into their two independent pieces unless it fits one of these exceptional cases. So here are two examples we can look at when we think about decomposition. I know it's a decomposition reaction because if I look at both of these cases, all I have is a compound. I don't have two reactants. So decomposition will always only have one reactant. If they're going to fall apart, they're going to fall apart into their component pieces, which means they're basically going to break up into their cation and their anion. So in this case with magnesium bonded to chlorine, magnesium is going to separate away from the chlorine. Now you have to consider what magnesium and what chlorine look like as a chemical compound because chlorine is one of our diatomics, so it's going to come apart as a 2. If you had something like sodium oxide falling apart into its component pieces, you would have sodium by itself, and again you'd have O2, which means you'd have to actually balance this chemical equation to figure out what the recipe is. Now this is one of your polyatomic cases again, so this chlorate would not break up into magnesium plus chlorate. That's not what we see happen. Instead, what we see happen is that we make a magnesium chloride, and the chemical formula is determined by charges, just like we did last unit. So crisscross, that's where I get MgCl2. And then these extra oxygens show up as oxygen gas. When you've gotten this far in predicting what the products are, you always need to come back in balance, because this is an incomplete recipe. We need to figure out how they actually react with one another. So if you look at this overall chemical equation and you were to count, which I'm not going to do, this chemical formula needs a 2. I wrote it wrong. So now if I did this over, I know I have 2 chlorines, but I have 6 oxygens. So I need more oxygens to make the chemical equation balanced, and then it is. So these are 3 complete balanced equations. The only information that's missing are states of matter, which really you can't get unless you're running a lab. So that's some piece of information we'd have to add later. Plan for in class is actually to practice predicting products and see a whole bunch of reactions that decompose to form smaller components. Have a nice night.